All right. So what is a Markov chain exactly? So the definition of a Markov chain, mathematically speaking, is defined by two objects. The first object is an initial condition given by a vector or a column matrix. And typically, if we are modeling something with n variables, that vector is going to be in our n, or if we're thinking about this as a matrix, this x0 is going to be a matrix with n rows and one column. And the next thing that defines mathematically a Markov chain, probably the most important part, is actually the Markov matrix M, which is a n by n matrix if you have n variables. So using the definition that we just introduced in the first part. So, and on top of it, for most examples, for us, typically the Markov matrix is going to be regular. And the way it works is that, so you're modeling some quantities that changes over time, and how do they evolve over time? Well, they evolve over time, or they're transformed over time by matrix multiplication. So you have the data at some point. So this is like what's going on right now at the Kate step. And then you have your transformer. Okay, so this is how this data that we have right now is going to be transformed, and it's going to be transformed by matrix multiplication. So a Markov chain is really a simple application. Well, I cannot say the word simple here, but it's an application of matrix multiplication. So matrix multiplication. And then what you get is the data after. Either the day after, the week after, the month after, the year after. Typically the K is an index, is a discrete index that depends on time. So depending on the context, so time can be in seconds, minutes, hours, days, weeks, months, years, etc. Okay, so it depends on the actual problem. But it's really a matrix multiplication. So normally in a Markov chain problem, so I wrote these as a remark here, if you want to model something with a Markov chain, the first thing you should be doing is to first label the variables. And here the variables, because they are changing, because the quantities are changing, these variables, they must be indexed by time. And this will become a bit more clear with my example after. And then after that, you need to use the information in the problem to model this Markov chain. And normally it's easier to do it first as a set of recursive linear equation. Again, I'll do an example in a moment to make this a bit clearer. But then once you have those equations set up, there's always a way to write that Markov chain in matrix form so that you can extract the Markov matrix out of that problem. And then with the initial data, you create your initial condition. And then you have your two objects that defines a Markov chain, the matrix and the initial condition. And typically the goal of a Markov chain is to study what's going to happen in the long run. So, you know, right now you have some cash, some people or whatever, and they're moving around, or it's moving around, and you want to know, well, if you let this go for a while, where are these things going to go without having to explicitly compute this Markov process or this Markov evolution over and over again. So like I said, the best way to really do it is to look at an example. So here we want to keep track of the money in a small country with a lot of problems, so probably run by the liberal government. So with government corruption, so the money moves between the people and the government. Every year it is estimated that 60% of people's money goes to the government through taxes or whatever, and then the government returns to the people 30% of what they have through whatever services or etc. Suppose that right now, so initially, the people have $5 billion and that the government has $1 billion. So we want to use a Markov chain to compute the amount of money of the people and the government in 2 years. And then if we let this Markov chain go for a while, we want to describe where is the money going to go eventually between the people and the government. Me personally, when I do a Markov chain, I like to summarize the information provided in the problem using this planet diagram. So what I mean by this is that, and this is just a remark here, you can do whatever you want as usual, as long as you understand and you can model your things on your own. But here, I like to draw two planets. Why two planets? Because here we have the people. So we have cash between the people and the government. And we want to model how is the money moving between the people and the government. So according to the data here, so first, we know that 60% of the people's money goes to government. So here, what I like to do is represent this information by an arrow, so that goes from the people to the government. So 60%. So I'm going to use, let's use a different color because we're fancy people here. So suppose people to the government. So 60%, I'm going to use the decimal value here. So 0.6 of whatever amount you have on the people planet goes to the government. So this means that the people are keeping 40%. So I like to draw this arrow from the people to the people, which is 0.4. And you can see that these two arrows coming out to the people planet sum up to 1. So this is kind of inducing the idea of having a Markov chain that will emerge out of this problem. And then what do we know also? We know that 30% of people's the government's money goes to the people. So if I draw this arrow from the government to the people, I get 0.3. So this means that these little MF, okay, they are keeping 70%. And again here, when I look at the numbers 0.7 plus 0.3, oh, this is my 1 year emerging. So like this is something I like to do. Again here, you don't need to do this. Okay, so this is just one way for me to summarize the information. And you'll see with my second problem in this section, actually the information is going to be represented with this little planet diagram. So it's good to be comfortable with it just in case I'm using it. So like I said, the first thing you do now, so for the solution, let's label the variables. So here we are looking at the money that evolves from 1 year to the next. So in K years, so my index is going to be K. So I'm going to put the money of the people and the money of the government in K years in one vector that I call XK. I'm always going to use XK in my example. So XK is the vector PK, GK, where PK is the money that the people will have in K years. So here, make sure that you understand that in these questions, when you are labeling the variables, there's a reference to the time year, the K, and then GK is going to be the amount of money the government has in K years, and this is going to be measured in billions to simplify things. So PK, how much money the people will have in K years, and GK, how much money the government will have in K years. So now let's construct the Markov chain in equation form. So it's always the same structure. So you're trying to compute what's going to happen next here. So PK plus 1 and GK plus 1. And here you just need to be organized. If you start with PK, all equations need to have like PK, with P, all the equations need to start with P. And if you are, because you could also do this and say, okay, I care about the government first. Like the order of the variable does not matter, but once you choose an order, you have to keep that order. So if you start with PK first, you can see that these two equations, they start with PK, and then you have your GK as the second variable. So how much money will the people get next year? So again, here I like to use the planet diagram. So from the people to the people. So this is like the same thing as asking, like, with this planet diagram, what are the arrows coming in? So the arrows coming in to the planet P, the people's planet, well, the people are going to keep 0.4. So next year, does not matter how much money you have right now. Next year, you will start with 40% of what you have right now. So you get 0.4 times what you have right now. And then you're receiving 30% of what the government is giving you, or whatever they have. Sorry, you're saying 30% of what they have right now. So how much money will the people get next year? Well, 40% of what they have plus 30% of what the government has. And now what about the government? Well, the government will receive, I'm going to use red here, will receive 60% of whatever the people have, so 60% of whatever the people have. And of course, they're going to have or keep, 70% of what they have right now. So next year, the government is going to receive 60% of people's sweet money and then keeping whatever they have. And that's an equation form. And again, here, very important. So if you start with P, you see that you have P as the first variable, and then you have your G variable as the second variable. So then it's only if you keep that order that this Markov chain can be rewritten in matrix form. So here, the left column is always next year. So in this case, I'm using K. So PK plus 1, GK plus 1 is next year. And now you see your Markov matrix M here. So you can see that if you look at the columns, 0.4 plus 0.6 and 0.3 plus 0.7, that sums up to 1. And make sure you feel this Markov matrix, the Markov chain in matrix 4. If you were to multiply this Markov matrix with PKGK, so as matrix multiplication, so if you take the column PKGK and you make it fall on M, you're going to recover the Markov chain, in equation 4. It's the exact same thing. It's just bullshit notation. Okay, so, but we need to see what is the Markov matrix. So here the Markov matrix is 0.4, 0.3, 0.6, 0.7. And by the way, it's regular because there's no zeros in that matrix. And of course, with that notation now, what is X0? Well, right now, the people have 5 billion and the government, 5 billions and the government has 1 billion. So that's my initial condition. And now the fun begins once you've modeled your Markov chain and your initial condition. Just by matrix multiplication, you can look at the evolution of the distribution of the money. So for example, how much money will the government and the people have in 1 year? Well, you just need to multiply X0 by M. So you do your matrix multiplication, the usual stuff. So dot product with 5.1 and 0.4 and 0.3 will give you 2.3. And then 5.1 with 0.6 and 0.7 will give you 3.7. A small remark here, if you look at the total amount of money, so 5 plus 6, that sums up to 6. And then the 2.3 plus 7, 3.7, gives you a 6 again. So one way to double check that you're doing the correct multiplication is that the total mass, it's probably not the right word to use here, but initially, like the total amount of money, like people plus government is 6. And then when it's being transferred, you still have $6 billion in total between the two entities. So anyway, so then in 2 years, now you take the freshly computed amount. So for X2, you go X1 times M. So again here, nice matrix multiplication. You can verify that it gives you 2.03 and 3.97. Again, this sums up to 6. And then as an exercise, if you compute X3, you get 2.003 and then 3.997. And then X4 is 2.003, 3.997. So by the way, what does that mean? It means that in 4 years, the people will have $2.003 billion, and then the government will have 3.9997 billion. Again, here, they all sum up to 6. So if you compute X5, you can double check that it's 2.00003 and then 3.99997. And then here we can start to see a pattern. If you let this go forever, you see these zeros. I had 1 0, 2 zeros, 3 zeros, 4 zeros. So you're going to have like more and more zeros after the dot. So you can see that these numbers, the 2.003 will eventually go to 2, and the 3.9999, etc., will eventually go to 4. So you can kind of predict that eventually, in the long time run, people will have $2 billion and the government will have $4 billion. So this Markov chain seems to stabilize to this amount of money. And actually this numerical behavior of getting this equilibrium forming up over this chain of matrix multiplication is very typical of a Markov chain where when M is, like in this example, regular. So just a bunch of remarks here to finish up or wrap up this example before studying this phenomenon a bit more in detail. So again, in my example, M was regular because all the entries, 0.4, 0.3, 0.6, and 0.7 were strictly positive. So that's the first thing to notice here. And that the next thing to notice is that eventually, so after letting the problem go for a while, eventually the amount of money were stabilizing to 2 billions and 4 billions. And like I mentioned earlier, the total amount was 6 billion. So when you talk about 2 over 6 here, so 1/3 of the total amount of money goes to the people, and then 4 over 6, that's 2/3 of the money that eventually goes to the government. And this creates then this information that eventually people will have 1/3 of the money and that the government will have like 2/3 of the money. If you take this distribution of 1/3 and 2/3, you can create this very special vector, okay, that we call Q. And this very special vector where you just put this eventual ratio. So here, 1/3 for the people and 2/3 for the government, has this very nice algebraic property that is such that if you take this vector Q and you multiply it by M, so if you do the matrix multiplication and do it, it feels so good when you do it. So if you take 1/3 and 2/3 and you take that column and you do the dot product on the rows, you will get again 1/3 and 2/3. So you will get again Q. So when you multiply Q by M, you get Q again. So it's like it's transformed, but it stays the same. So this vector is very, very special for a couple of reasons. The first thing is when you look at the sum of the entry, 1/3 plus 2/3, well, it sums up to 1. And it is also such that when you multiply Q, this vector Q, by M, you get Q again. And a vector like this is a very special vector. It's called a steady state vector. We'll go over the definition in my next part. But this Q vector is called a steady state vector for the Markov matrix. And for us, the steady state vector will be so crucial because it will be the key to foresee the future of this Markov chain. It's so beautiful. All right. That's it for now.